All right, you should be at the bottom of page 5 with me. And so we are talking about the strength of acids, bases, conjugate acids, and conjugate bases. The only thing you need to remember about this is pretty much its opposite. So the stronger the acid, then the weaker its conjugate base. And I could say that the other way too, that the stronger the base, then the weaker its conjugate acid. So it works both ways. All right, so how can I tell the strength of an acid? Well, first of all, you should know which ones your strongest are, because there's 6 of them. All right, we just went over them. HCl, HBr, HI, H2SO4, HNO3, HClO4. So those are your 6 that are strong. So therefore, you know their conjugate bases are going to be the weakest. Okay, so flip with me for just a second. We're going to kind of do this backwards. All right. So let's go to example 3, exercise 3. So you're flipping all the way to page 7. Right, and we're looking at exercise 3. So this says to use table 14.2, which we're going to use in just a second, but let's pretend like we don't know the table yet. Arrange the following species according to their strength as bases. So what I want you to do is I want you to start with the weakest. Okay? So looking at these here, okay, 1, 2, 3, 4, 5 of them, right? Which one of these is going to be the weakest base? Cl negative. How do I know that Cl negative is going to be the weakest base? Excellent. Thank you, Katie. Because HCl is a what? Strong acid. Is HF a strong acid? No. Is HNO3, HNO2 a strong acid? No. Is HCN a strong acid? No. So all of these bases, F negative, NO2 negative, Cn negative, are going to be stronger bases than Cl negative. Do we see that? Okay. So I automatically know that Cl negative is going to be the weakest. Do we see that? After that, I'll go ahead and tell you, is going to come H2O. Okay? How do I know that H2O is going to come next? Because H2O is what? Neutral, right? So it's going to kind of be the break between my strong acid here and then my weak acids, which have become bases there. Does this make sense? All right? So they were in that order. So now, how will I be able to tell which comes next, F negative, NO2 negative, or Cn negative? Do we know anything about those? No, we don't. So to be able to do that, we've got to come look at table 14.2. Yes, this would have been given to you on a test. You wouldn't have to know this off the top of your head. Right? So if we look at table 14.2, and I look at my Ka values, okay? The larger your Ka value, that means the what the acid? The stronger the acid. So the larger the Ka, then that means the acid is stronger. So let's find the ones that are on our exercise 3. I've got HF, HNO2, and HCN. Okay? So which one of these is strongest out of the 3? HF, HNO2, or HCN? HF. So that means the base of HF, the conjugate base, F negative, is going to be what compared to NO2 negative and Cn negative? It's going to be weaker, right? Because HF is stronger than these, so the F negative is going to be weaker. Do we see that? So the next in line would be F negative, then NO2 negative, and then my Cn negative would be the what base? The strongest base. Do we see that? So let me go down here and do this. Does this make sense to everybody? Nod your head with me if you're with me. All right. So now flip back. I know we're going backwards and skipping all around, but it just makes more sense to do it that way. So if we look here, I'm back at the bottom of page 5. All right. So if I have a strong acid, my Ka value is going to be large. Okay? So if I have a large Ka, that means I have a strong acid, and it means my conjugate base is going to be what? Weak. Okay? If my Ka value is small, that means I'm going to have a weak acid, which means my conjugate base is going to be strong. Do we see that? You're with me? Excellent. Now we can go back to being in order. All right, the majority of acids and bases are weak, and this should make sense to you, all right? Because how many strong acids do we have? 6. So that means every other acid in the world is considered to be weak, okay? Right, and then we think about our strong bases, okay? How many strong bases do we have? Everything in column 1 and everything in column 2 that's bonded to the hydroxide with the exception of what? Beryllium and magnesium, okay? Those are my only strong bases. So everything else is considered to be a weak base. So almost everything, as far as acids and bases are concerned, are considered to be weak. So most of the stuff we do are going to involve weak bases and weak acids. Okay? So let's talk about writing equilibrium expressions. Please don't let this throw you. We already know how to write an equilibrium expression. What is big K equal to? Products over reactants. Okay, so the concentration of products over the concentration of reactants. Now we're going to learn how to write an expression for Ka, and it's called the acid dissociation constant. Okay, it's the same thing as a regular K, except now we just added a little a to let me know I'm working with acids. Okay, I changed nothing. It's still concentration of products over concentration of reactants. Okay. Now, for weak acid reactions, I have HA. This lets me know it's the acid, okay? A stands for acid, and then acids always have a what in front of them?
Hydrogen.
Hydrogen. So there's my acid, which means water is acting as my base. Acids do what with the proton? Donate it. Bases accept. So now my H3O positive becomes my, and my anion, what's an anion? A negative ion. This becomes my conjugate base. So if I asked you to write the Ka expression for it, okay, you would just do the concentration of your products, H3O positive, times the concentration of A negative, divided by the concentration of your reactant, which is HA negative, just HA. Why did I leave water out? Because it's a liquid. You tell me. Because water is a liquid, and who does not get included in our equilibrium expressions? Solids and liquids. So water, H2O is a liquid, but we also wouldn't include solids. Okay. So no solids, no liquids included in our equilibrium expression. Now, this is a weak acid. We said we were writing the Ka expression for a weak acid. How do I know that it's going to be much less than 1? Weak acids do not do what? Dissociate. Okay? So when I took this acid and tried to break it apart, most of it stayed as a what? Reactant. Only very little of it dissociated. Do we see this? Okay? When I take a big number, or when I take a small number, and I divide it by a big number, what kind of number am I going to get? A really small one, right? Do we see this? Okay. So, right here, it says it wants us to write the Ka expression for acetic acid. Okay. Well, before I can write the Ka expression, I've got to know what acetic acid is. What ion does acetic acid come from? Acetate. Okay, it comes from acetate, which is C2H3O2 negative. But to make it an acid, I do what? Add an H there, so it cancels out the charge. Okay. we're going to try to dissociate this acid in what? Water. So here's my acid, here's my base. My acid does what?
It's the HOA.
It's the HOA. So I end up with H3O positive, which is going to be called my conjugate acid, plus C2H3O2 negative, which is my conjugate base. So can I write a Ka expression for this?
Yeah.
Yes. How do I write Ka? So tell me what it's going to be. Concentration of H3O positive times the concentration of divided by the concentration of,
HC2H3O2.
and why am I not including water? Because it's a liquid.
Will we ever include water? Will it ever give us 2 cents of gas?
No, not for Ka and Kb. It'll never be given to you as a gas. It'll always assume for an acid-base reaction it's liquid. Because remember, we're trying to get the acid to dissociate. It wouldn't dissociate in a gas or a solid. It would only dissociate in the liquid. Good question, then. All right, weak bases react with water to produce a hydroxide ion. So now we're moving from weak acids and we're talking about weak bases. Okay. Common examples of weak bases are ammonia, which is NH3. If you have not memorized that A, ammonia is NH3, you need to do it. And B, that it is a weak base, you need to know that as well. Okay, so you need to know ammonia is NH3 and NH3 is a weak base. Okay, so make sure that you know that. Another example would be your methylamine. Now you do not have to know this, okay, because you do not have to know organic, but just so you don't get on the AP exam and freak out, okay? Meth, last year, when we talked about that, when we named, is how many carbons? 1 carbon. Not meth, the drug meth. Come on, Jim. Okay. Meth, the hydrocarbon, okay? Eth means there's how many carbons there? 2, okay? So prop means there's how many? 3. And then bute means there's how many? 4. And then the rest of them go with your regular prefixes. 5 would be pent, 6 would be hex, 7 would be sept, 8 would be oct. You get where I'm going with this, okay? Now again, don't get bogged down with this. I just want you to see it, okay? So you're not freaking out about it. So methyl means I've got a group with 1 carbon. So there's my CH, whoops, there's my CH3. Let's not bond that hydrogen there. Let's bond the hydrogen. Okay. Now it's bonded to an amine group. An amine just means there's a nitrogen there. Okay. So I show it bonded to the nitrogen. Nitrogen always has that lone pair, which means how many spots are available for extra hydrogens to bond to now? 2. So 1 there, 1 there. So that would be a methylamine. Okay? And ethylamine would be the same thing, except instead of having 1 carbon, now I have 2 carbons. Do we see this? Okay? And again, you don't have to know that. I just sometimes if you have basic knowledge, it keeps you from freaking out on an exam. Okay? That's right. We're going to erase this. Alright, so here is ammonia, NH3. Already know that ammonia is a what? Weak base. So I know this is my base. This is happening in water. So water is going to act as my acid. Okay. Alright, my acid donates my hydrogen. Why is it donating my hydrogen here? Because this hydrogen is attracted to the what? That lone pair on this nitrogen. So then I get ammonium, which is NH4 positive, and that's going to be my what? Conjugate acid, plus OH negative, which is going to be my conjugate base. When I see this OH negative, I know I'm working with what kind of solution? a basic solution. Okay? That OH negative is my key that this is a basic solution. So when I write my expression, would I call it KB or KA? KB. Okay? I would call it KB. So could you write your expression for KB?
Absolutely.
Absolutely. How would I write my expression for KB?
I'm getting them.
It's innate, yeah. Concentrated OH.
Over NH3. And then not H2O because it's a liquid.
There you go. And I would not include H2O because it is a liquid. Do we see this?
Yes.
We feel comfortable with this? Yes? All right. And that's all this next page, page 7, all right, is saying that when we have an equilibrium expression for bases, known as KB, okay, have my base plus my H2O, gives me my conjugate acid plus my conjugate base. When I write the KB expression, it's still products over reactants. I don't include water because it's a liquid. And if it's a weak base, I know this should be much less than 1. Because if it's a weak base, it's not going to what? Dissociate. So I'm going to be left with a lot more product than I have reactant. We already wrote the KB expression for ammonia when we wrote the equation a few minutes ago. All right. Notice Ka and KB expressions look very similar. Okay, they're pretty much the same. The only difference is a base produces which ion? Hydroxide. And acid produces what? Hydronium. And hydronium is H3O positive. Sometimes instead of writing H3O positive, we'll write H positive, which is fine. They are both equivalent. Okay, so if you see H3O positive or if you see H positive, it means the same thing. You with me? Excellent. Moving on, page 8. All right, auto-ionization is what we're going to talk about first. Okay, if I put something on autopilot, it means it happens how?
Automatically.
By itself. Okay, it automatically happens by itself. Water has the ability to auto-ionize itself. What does it mean for something to become ionized? It becomes an ion, and ions are called what? What kind of particles are ions? Negative or positive. Okay? All right. Ions are just charged particles. So for something to have the ability to auto-ionize, it just means it can combine with itself to make charges. Okay? So again, remember, water can be considered an acid or a what? Base. It could be either one. So, since it can be either one, it can cause itself to become charged. One water molecule can donate a hydrogen to another. Okay. Then we get H3O positive, which would be my conjugate acid. We get OH negative, which would be my conjugate base. So two neutral molecules manage to turn themselves into a positive ion and a negative ion. So that's what we mean by water can auto-ionize itself. Do we see this?
Is that with anything else? Or is water?
Just water.
So we take it.
Now, only about 2 in a billion water molecules can be ionized at any instant. So does it happen often?
Probably not.
No. Okay, 2 in a billion aren't great odds there. Okay, 2 in a billion are not great odds there at all. So don't get stuck on that one. Okay. So this leads us to our KW expression. Notice we're real creative as chemists. Ka is for acids. Kb is for bases. So Kw is going to be for water. Okay. We're super creative here. Okay, so this is the auto-ionization constant for water, which is Kw. All Alright, this is important for us to get. Okay. At 25 degrees Celsius, and this is important. You need to make sure that this works at 25 degrees Celsius. At 25 degrees Celsius, Kw is equal to 1.0 times 10 to the negative 14th. Okay? Don't worry about that 8 right there. That's not important. Okay. Kw is also equal to the concentration of H positive times the concentration of OH negative. Okay. And then we're not going to use this one for a little bit, but we'll eventually come back to it. Kw is equal to Ka times Kb. What I really want you to focus on right now are these two.
So that's only at 25 degrees Celsius.
Only at 25 degrees Celsius is Kw equal to 1.00 times 10 to the negative 14th. We're about to look at exercise 5, and you'll see when we change the temperature, we change the value. But it does not change the fact that Kw is equal to this times this. Okay, that doesn't change. All right, knowing this means that we can calculate the concentration of hydroxide and hydrogen in almost any situation. And we'll get to that in just a second. So, if the concentration of hydroxide is equal to the concentration of hydrogen, then I know the solution is neutral. Okay? If hydroxide is greater than hydrogen, then the solution is basic. If hydroxide is less than hydrogen, the solution is acidic. That's all we need to know. So let's look at exercise 5. At 60 degrees Celsius, this is going to be important for you to notice. So make sure you notice that this is at 60 degrees Celsius. The value of Kw is 1 times 10 to the negative 13. So A says, using Le Chatelier's principle, predict whether the reaction below is exothermic or endothermic. So, notice, I know my value of Kw at what temperature? 25 degrees Celsius. What did I do to my temperature in this problem? I increased it. So I know my temperature increased. What happened to my value of K when my temperature increased? It went up as well, right? Negative 13 is greater than negative 14. So my Kw also increased. So, did my products increase or decrease?
Product should increase. You're adding it.
My products increase, right?
Yeah.
Hang on, I'll show you. How do I know? K is equal to what? The concentration of products over the concentration of reactants. So if my K value went up, what else had to go up? My products had to go up to make this number bigger, right? Okay? So that means my products had to have increased. So reactants went down, products increased, okay? In order to get equilibrium to shift towards the products, I had to have added my heat to what side? The reactant side. So that means I added heat as a reactant. When we add heat as a reactant, what kind of reaction is it? Endothermic. Do we see how to think through that? Yes? So B says calculate the concentration of hydrogen and hydroxide in a neutral solution at 60 degrees Celsius. What do I know about hydrogen and hydroxide in a neutral solution? That they're the same, correct? They have the same concentration. Do I know, so I know that Kw is equal to the concentration of H plus times the concentration of OH negative. Do I know my value of Kw at 60 degrees Celsius? Yes, it told me up there. It's what? 1 times 10 to the negative 13th, right? So that's going to be equal to my concentration of hydrogen and my concentration of hydroxide. And these both have to be the what? Same in order for it to be a neutral solution. So I can call both of these what?
X.
X. Can I solve for X?
Yes.
Yes. That means 1 times 10 to the negative 13th would be equal to X squared. How do I get X?
Square root of.
Square root it.
Square root.
And if you take the square root of that, how many sig figs is this?
1.
1. So how many sig figs need to be in my answer?
1.
1. So then I get 3 times 10 to the negative 7 for my answer. You with me so far? We're good? Alright. Next page. I'm on page 9. The goal is to get somewhere on page 10 and I'll be happy. Alright, page 9. Let's talk about the pH scale. The pH scale goes between what?
1
0 to
14.
14, all right? The pH scale goes from 0 to 14, where if the pH is between 0 and 6.999, the solution is considered to be
6.
acidic. If it's 7.0 on the dot, the solution is neutral. And if it's above 7, the solution is
Basic.
basic. Okay? So how do I find my pH? If I know the concentration of my hydrogen ion, then I know that pH is equal to opposite the log of H positive. Because if you take the log of a positive number, it's going to give you what kind of number? A negative. Okay, so we take the opposite of that, so I want my pH to be what? Positive. Okay? So to get the POH, I take opposite the log of my concentration of hydroxide. Okay? And if I add my pH plus my POH, I should always get 14, because that's what the scale goes up to. Okay? You need to know these 3 equations. All right, how do we do sig figs for pH? All right. We take the least accurate measurement. So we take the least number of sig figs in the problem. So let's pretend like this is the least number of sig figs. How many sig figs is 1.15? 3. Okay. So I go to the least accurate measurement, and then I report my pH in that many decimal places. So how many decimal places would I need in the pH of this? 3. Okay. And we'll practice with that. All right, as we go. So let's go to exercise 6. It says calculate either the concentration of hydrogen or the concentration of hydroxide from the information given for the following solutions at 25 degrees Celsius and state whether the solution is neutral, acidic, or basic. Right? So let's look at A. A gives me my concentration of what?
Your hydroxide.
Of my hydroxide, so that means I'm looking for my concentration of H plus, right? Okay. So I want to know what my concentration of H plus is. Well, what do I know? Do I know an equation that involves H plus and OH negative?
Yes, we do.
Yes, what equation is that?
Okay,
There you go. Kw is equal to the concentration of H plus times the concentration of OH negative. Correct?
Yes.
Correct. Do I know what Kw is at 25 degrees Celsius?
Yes.
Yes, what is it?
It is 1.00 times 10 to the negative 14.
Excellent. I don't know my concentration of hydrogen. That's what I'm trying to find. Do I know my concentration of hydroxide?
Yes.
Yes, they gave it to me. It is 1.0 times 10 to the negative 5th. How do I solve for my concentration of hydrogen?
Divide.
Divide. So do this divided by this. One divided by one is 1. How many sig figs do I need here?
2.
2. I'll make that 1.0 times. When I divide my exponents, I do what?
You subtract.
Subtract them. So negative 14 minus a negative 5 would give me a what? Negative 9. So there's my concentration of my hydrogen ion. Which one is greater, my concentration of hydroxide or my concentration of hydrogen? Hydroxide. So is this solution basic or acidic? Basic. And we should feel comfortable with this. Okay. All right, B, again, they give me my concentration of hydroxide, so I have to find my concentration of hydrogen. So, I have 1.0, so I write out the same thing. Kw is equal to 1.00 times 10 to the negative 14, which is equal to my concentration of hydrogen, which I'm solving for, times my concentration of hydroxide, which they gave me. 1.0 times 10 to the negative 7th. So then I just divide. So my concentration of hydrogen is equal to what? To the negative 7th. These concentrations between the two of these are what? Equal. So that means this solution is what? All right, let's look at C. C now gives me the concentration of what? My hydrogen. So now I've got to find my concentration of hydroxide. Okay? I'm going to change this to where it's in scientific notation, so I can do it without a calculator. Okay? So 10 would be the same thing as 1.0 times 10 to the first. So Kw is 1.00 times 10 to the negative 14, which is equal to, I know my concentration of hydrogen, 1.0 times 10 to the first, times my concentration of hydroxide, I don't know. So now I'm just going to divide. So my concentration of hydroxide is equal to what? So which one has a greater concentration, hydrogen or hydroxide? Hydrogen.
So this is acidic.
So that means this is acidic.
This is basically just adding the last two numbers.
It's very easy.
You said we're not going to do this more.
No, we're not having a quiz on this one. We will Wednesday though. Whoop, whoop. All right, let's look at exercise 7 and then we'll call it a day. All right, exercise 7 says calculate the pH and the pOH for each of the following solutions at 25 degrees Celsius. Okay. Now, what is my equation for pH?
It's the negative log of the hydrogen.
There you go. And my equation for pOH is
Times the hydroxide.
my hydroxide. And so my pH plus my pOH is equal to what? 14. So should we be able to figure all of this out? Yes. Since they give me the concentration of my hydroxide, what does it make sense to find first?
Your hydroxide. Or the pH.
The pOH, right? So I'm going to say pOH is going to be equal to opposite the log of 1.0 times 10 to the negative 3. Okay? Now, put this in your calculator. If you put in 1.0 EE negative 3 and you hit the log, what does it give you?
Log,
Mm-hmm.
It's a long period.
When you hit the log button, what number comes up?
negative 3.
-3, which coincidentally is the same as my what?
Exponent.
Exponent. Okay? If I have 1 times 10 raised to something, remember log is base 10, it's just going to be whatever my exponent is. But we take the what of that?
The opposite.
The opposite. So my POH is equal to what?
3.
3. How many sig figs are here?
1, 2,
2. So how many decimal places do I need?
2.
2. So this should be 3.00. So now that that's my POH, can I find my pH? How do I find my pH?
14 minus 3.
Just do 14 minus 3. So my pH would be equal to what?
11.
11, and make sure you have those 2 decimal places for those 2 sig figs. Is this a basic or an acidic solution? It's basic, because my pH is what? 11. Anything greater than 7 means I'm what? Basic. Now, B gives me my concentration of what? My hydrogen. So it makes sense to find my what? pH. So pH is equal to opposite the log of 1.0. What is the log of 1.0? 0. So my pH is equal to 0. How many sig figs are there? 2. So how many decimal places do I need? 2. So I add 2 zeros. So what is my POH? 14. Because 14 minus 0 is 14. Do we see this? Alright, we'll wrap it up there and we'll start with exercise 8 tomorrow.